And our presenter is Zhen, and he'll be talking about wing crack dynamics in silica glass.
Today, I'd like to talk about wing crack dynamics in silica glass. So this is a simulation work, and the system we used include 15 million items. So this is the outline of my talk. After introducing the problem, and our motivations for this study, I'll briefly describe the molecular dynamics simulation method we use, and then let's look at the results. So, under multi-axial compression, when correct, we group when cracks, secondary cracks emanate from the pre-crack tip under multi-axial compression. So this is an experimental picture by Bragg and one more like this. Continuum models have been created for wing cracks assuming pretty static fluid. Here, we have a material with a pre-crack of length 2A and apply multi-axial compression. And here, assuming sigma 1 is larger than sigma 2. And then wing cracks will initiate under certain conditions from the tip of crack tip, pre-crack tip. This is done by frictional sliding of two surfaces of the pre-crack. So this side moves towards this direction, and this side moves towards this direction. This motion would generate tension at crack tip. Then theta is the angle between the initial wing crack and the pre-crack. And it's predicted to be 70.5 degrees. Then wing crack will grow and turns into the direction of maximum compression. In this case, it's the direction sigma 1. So recently, people have been putting efforts to study wing cracks under dynamic compression. So Lee and Rajiv work concentrated on the dynamic wing crack behavior using photoelasticity. And Joe Rosakis and Rajiv has done a lot of work under the condition of impact loading. And they also measure the local stress distribution ahead of crack tip. Rico's work focused on the thermal effects of wing crack. So, intrigued by this experiment, we decided to perform. I really want to do this. Okay. Intrigued by this experiment, we decided to do a simulation on wing cracks, and these are the issues we want to address by our simulation. So, what's the initiation growth mechanism? How is the local property, such as stress and temperature? What's the effect of confinement? In the next two slides, I'll briefly describe the method we use. So within molecular dynamic methods, we consider a system of n atoms, and we solve Newton's equation of motion numerically. The major input is the interatomic potential. For silica, we use the potential developed by Dr. Priya Vashishta. And the two-body terms include steric repulsion, screened polar interaction, and charged dipole interaction. Three-body terms reflect covalent bond bending and cracking. The validation of this potential is being done by comparing MD results with experiments. The left is a figure of neutron scattering experiment results and MD results. We can see fits quite nicely. On the right is a table comparing the dynamic properties with this experiment. They also agree. So here is the simulation setup. The blue region is silica glass with a pre-crack. And then the impactors, we used a rigid impactor. We did 2 simulations, and the impactor speed choosing to be 150 and 375 meters per second. Okay, now let's look at the result. I have to explain the color. The light blue represents the void region that is connected to the pre-crack. So if there's a wind crack and it's connected to the pre-crack, then it's also shown to be light blue. Other colors like red, green, yellow, orange, these are the void regions that are not connected to the pre-crack. So they represent nanocavities. Let me write it again. So as you can see here, when crack initiates with cavities, and then it tends to the direction of impact. And then it is stopped in the end, and there is a healing. So this is the result for 375 meters per second impact speed. This is the movie for the impactor speed 150 meters per second. As you can see, in the beginning, the beginning stage is very similar to what happened at 375 meters per second. But then the following behavior of wind crack is different. So you can see the healing of the wind crack, and then it starts again, grow longer, and this pattern repeated. And there's a healing. Then it will grow again. And also we can see the damage in front of the pre-crack here, and also in front of the wing crack. So, since we are especially interested in the initiation stage of wing crack, so we measured, in this case, calculated the stress distribution ahead of the wing crack tip. So this is the result. The prime coordinate is rotated 70 degrees around the axis. So x prime would be the initiation direction of the wing crack, and the sigma y prime is perpendicular to the direction of wing crack initiation. So as we can see here, there are 3 stress maximum corresponding to these 3 regions. Okay. So this tensile stress is a tensile stress. So this is caused by the frictional sliding of pre-crack surfaces. But this result actually is different from a continuum model, because in that case it's a 2D picture. So there's no z-axis here, and here we see the wing crack actually started from 3 different positions. And well, actually, at this stage, it's still nanocolumns. And let's see how wing crack forms. So we have these nanocolumns caused by the frictional sliding, and then nanocavities are formed. And then the nanocolumns grow, and the cavities coalesce with each other and merge with these nanocolumns. And then all these combined together become a wing crack. So this picture is different from a continuum model, and I think this is one of the major results of this research. But surprisingly, the direction of the initial wing crack is also, in our case, 70 degrees. And it agrees with the continuum model, which is a surprising result, because our picture is different from continuum model. This is a figure for the temperature distribution. So x prime is the distance from the wing crack tip, from the wing crack tip, and delta T is the temperature change. So temperature increase roughly inverse proportional to the distance. And also, this agrees with theoretical prediction made by Rice and Levy. This slide illustrates the heating of the wing crack. So after turns toward the direction of impact, it stops, and then heating starts. At 45 picoseconds, a stress wave reflected from side walls split off a cavity. The length of this cavity is about 20 nanometers. And after passage of the stress gauge, the healing continues. Okay, so here's a brief summary of my talk. We performed the MD simulation on silica glass to simulate the crack. And we compared our results with experiments and continuum model. And we found nanocavitation is a major growth mechanism causing crack. And we also obtained local properties. I'd like to thank my advisor, Dr. Rajiv Kalia, Achiro Nakano, and Priya Vashishta. And also thank to my colleagues, especially Zhen, Pingqi, Ashish, Liang, and our collaborators in France, Elizabeth, and Singh. Also our founder, Rafa,